Chapter 6, Part 5. Factors affecting the rates of SN1 and SN2 reactions. The strength and concentration of the nucleophile will be the focus of this video. So first let's discuss the strength of the nucleophile. An SN2 reaction needs a strong nucleophile. It needs to be strong enough that it's going to kick out the leaving group and will not act as a base. So for example, in this reaction, chloroethane reacts with a thiolate, which is a deprotonated thiol, or the conjugate base of a thiol, to form a thioether and chloride. A thiolate is a very good nucleophile. It has a concentrated negative charge. It's fairly small, and it's able to do the backside attack that we need it to do. It's also not a particularly strong base, so it's not going to be tempted to act as a base, which would do the chemistry that we're going to look at in Chapter 7. SN1 reactions don't really require a strong nucleophile. You can use a weak nucleophile because the first step of an SN1 reaction is to create an excellent electrophile first, and that is the carbocation. So if you are forming a really great electrophile, then you can use a weaker nucleophile. Also, SN1 reactions often need a weak nucleophile because if you have a nucleophile that is too strong, it might actually attempt to do an SN2 reaction before the carbocation can form. A strong nucleophile may also perform an elimination reaction, which is in Chapter 7, if it is also a good base. So in this example below, this is actually using tert-butyl alcohol in acid, although the acid is not pictured, to form a good leaving group, which can then leave and create the carbocation. Now at this point, anything would be a good enough nucleophile to attack this. So in this example, we used methanol. Notice the difference between the two nucleophiles that we've used in these examples. Oxygen and sulfur are fairly equivalent as far as nucleophiles and bases go, but the thiolate has a negative charge on it, which is going to make it a stronger nucleophile than methanol is because it's neutral. So what makes a good nucleophile? First, our big rule here. A negatively charged nucleophile is always more reactive than its conjugate acid. So for example, hydroxide is more nucleophilic than water, which is the conjugate acid of hydroxide. If you're comparing nucleophiles that have the same nucleophilic atom, the nucleophilicity is going to parallel the basicity. So for example, an alkoxide is more nucleophilic than hydroxide, because an alkoxide is more basic than hydroxide. In this case, the nucleophilic atom is the oxygen. And then looking at this carboxylate here, a carboxylate is less basic than hydroxide, so it's also not as good of a nucleophile as hydroxide. And then you have two neutral molecules here, which are de facto the weaker nucleophiles compared to our negatively charged species. When nucleophilic atoms are different, there is no parallel with basicity. The rules kind of go out the window, and you just kind of have to know what is a good nucleophile and what is not. A couple of good examples here. A thiolate is a pretty dang good nucleophile. It's one of the best options. Cyanide is a really good nucleophile. Halogens are good nucleophiles, and so is hydroxide. But hydroxide also has a tendency to act as a base. Another thing to point out here is that hydroxide is actually the strongest base in this entire list, and yet it's the worst nucleophile. So even though we want nucleophilicity in general to mimic basicity, it actually doesn't, because the ability of a molecule to act as a nucleophile is something that's actually determined experimentally and not theoretically. So we know that these molecules are good nucleophiles because somebody did reactions that proved it. Basicity is related to the equilibrium of an acid-base reaction. That is something that is a known fact, and you can observe it experimentally, but it also relates to the pK value. Another factor is the concentration of the nucleophile. In an SN1 reaction, there is no effect of the concentration of the nucleophile. If you want an SN1 reaction to go faster, you need to have a better leaving group. You can increase the concentration of the nucleophile all you want, but it's not going to speed up an SN1 reaction. All that's going to happen is that you may possibly favor an alternate reaction. In an SN2 reaction, you can actually increase the rate of the reaction by increasing the concentration of the nucleophile. And that's because the concentration of the nucleophile is in fact a multiplier in the rate law of the SN2 reaction. So simply stated, if you increase the concentration of the nucleophile, you also increase the rate of the SN2 reaction.